Okay, hello, welcome back to another one of my video log recording sessions where I talk about genetic algorithms. Date, time is 2025 May 21st, and the time is 20 past 1 a.m. in the morning. So, wow. I have no idea why I just said wow. So, well, today I'm definitely not going to be covering 13 notebooks like I did last time. Today I'm just going to be covering the results that I got from one notebook. I mean, granted, the notebook in question did generate 64 resulting folders or directories, but yeah, it's still from one notebook with a clear objective in mind, and that objective being, well, I wanted to find out what would happen if what I have done so far with the new, better evolution scheme and the learn function and the candidates function, with the concepts of learning and candidacy or candidacy. I wanted to see if similar results. What? What was it? What am I using? Oh, this was a brush. So sorry, I got distracted. So I wanted to see if I could get similar results if I moved away from preset values to general values. Now, the difference between these two is that if, for example, if I say that items, utility values and constraint values were preset, what I mean by that is that they were determined beforehand. So determined beforehand by a person, for example. But and you might say, well, isn't that always the case? Not exactly. If you compare what goes on when I do things the general way. Now, in the general genetic algorithm way, I don't know if all of this is official or not, but at least the way I did it is that if it's called general, what I do is I generate the values. I generate the items and their utility values and their constraint values, which come from a certain distribution. It may come from any one of these distributions. Something like that. So there are the utility values and the constraint values, CST, and these two sets could come from the same distribution, but they would still be sampled separately. So they're not the same value. Just because they're from the same distribution type does not mean that they are the same value. And if they're not sampled from the same distribution, for example, something like this, well, then of course they are different. So that's what's happening, and I've also I had also explained this in one of my previous videos, in more than one of my previous videos, about 2 months ago maybe. But anyway, I felt like going through that again. So if I were doing things in the general way, there are 8 types of distributions. There's no normal, log normal, uniform, I can't spell, exponential, I'll just put exponential, expo, what was it, Mises, I think, and then there's Pareto, that's 6, and then there's Fable, and then last, left skewed. So 8 things to choose from for 2 sets. That naturally gives us times 8, which actually, yeah, it naturally gives us 64 combinations, because it could be, the utility values could be normal, and then the constraint values could also be normal, but the utility value could also be normal, and then constraint value could be uniform. So there are 8 times 8 equals 64 combinations, and therefore I needed to do 64 times something. Now, what is something? That something is the combination of learn methods, or well, not plural, one learn method and one candidate method with a candidate percentage, which in my last video I decided that it will be 0.2. So 20% of the world within a generation will be chosen as learning candidates, as candidates for learning. And I mean, it's not going to be the bottom 20. However, it is going to be the distribution of chances, or the distribution of probabilities for entities in the world is going to favor the tail entities. So this is the head, this is the tail. Head is the top entity with the highest summed utility value, tail is the bottom entity with the lowest summed utility value. And the distribution of probabilities of being chosen as learn candidates is going to favor the tail entity. So it's going to be like this. Well, now they are the weights, and with these weights they're going to be sampled without replacing. So 20% of entities are going to be chosen, and this favoring the tail is well, I call that the favoring tail, but since this shape is exponential, I call that exponential tail. That is the candidate method. Now for the learn method, learn rate method, not learning rate, not to be confused with learning rate in deep learning. So this is just learn rate. It's I know it's confusing and sometimes quite hard to say, but anyway, it's quite similar. But in this case, the learn rates are, well, calculated and assigned by, again, looking at the world and the ranks of entities within the world before shuffling. The learn rates are also going to favor why am I? Oh my god. The learn rates are also going to favor tail entities, or entities towards a tail in this case, but it's not going to be like that. No, that's a big no-no. It is not going to be an exponential curve skewed to the left, because this way only the tail entity has 100% chance of learning, and then the next bottom one will have a 50. Was it 50? I think it was 33 the way I did it. And then the one after that will have a 20% chance of success in learning. So that's bad. So instead of this, I implemented the... Does that show? No. I implemented a proportional or proportionate way of assigning learn rates, and well, it actually is a lot simpler than doing the exponential curve, as the tail entity will now have again 1.0 chance, which means 100%, and then the next one in line, the second one from the bottom, will have something like if there are 50 entities within the world, for example, then the next one is going to have 98% chance of success. The third one from the bottom will have a 96%. So imagine if there were 1,000 entities within the world, the tail entity will have again 100% chance. The one after that, let me just put that. I think the tail one will have a 1.0 chance, meaning 100%. The second one from the bottom now will have 0.9998, I think. Was it? Is that right? Or is it 98? Yeah, I think this is right. I can't do math right now, I'm just so tired. Maybe I'm bad at math. But anyway, maths aside, that's how it is. And then the third one will have 0.9996 chance, so which is 99.996. Oh, I'm missing another 9. Yeah. So the learn rate gradually falls off, instead of this drastic decrease as the rank goes up or down. In any case, in either way, when I do it proportional or proportionate, the learn rate will decrease quite gradually, like a gradient. So that's why I chose, because if this happens, it doesn't matter if you get chosen or not. If the learn rate just drastically goes down to like 10% or 5%, however many, it doesn't matter how many entities I choose. If I do this, even if I choose 100% through the candidate method, learn rate candidacy method, if the learn rate is like this, abysmal, then it's not really going to matter. So I talked about this in my last video, I should cut it short. So learn rate method, proportional tail, tail, and candidate method is expo tail, with the candidate percentage being 0.2, as in 20%. So that's what is going. that's what is going to be shown, because that's what I've done. Let me just do this again. LRM is propo tail, and candidate method is expo tail, and candidate percentage is 0.2. I should just put that in one line, and I do this 64 times. So whenever I have a group of plots, I would have k times 64 plots, which is exactly what I'm going to show you. It's going to be 64 plots, or 128 plots, whatever. I really should go to sleep. I can't do simple maths. Anyway, so notebook. This is the notebook that I used to generate it. Just quickly, if I were to quickly just go through it, there you go. There you have the 64 combinations that I did, and come on. And I have the assigned learn rate. I have the candidate list, and then I know it's then I also shuffle, and I also know that my code is just horrible. Even when I look at it, it's horrible. And that's about it, really. No, create percentage, 0%. The initial population is always set to 10, and well, for the past month, the procreate function that I've been using is, well, it's always been what was it? It's always been favoring highs. I know that oligopoly is better than favoring high in terms of some utility values, but I just did not like the idea of the top something percent procreating while the rest don't. I mean, now that entities also learn, I mean, the use of this could may be justified, but I'm still sticking to this. And I've also fixed all the procreate functions so that they could be used for tracking individual entities. So when all the evolutions were done, 64 iterations were done, I got left with 64 folders, and this time I'm not going to not going to have a look at the lifespans or the slopes. Well, at least not for now. Today I'm just going to show the entity distributions and the average summed utility plots for the world. So this is what it looks like all in one, but since this is hard to just actually see anything, well, first I should do this. So within each iteration of evolution, the items and the utility values and the constraint values would be generated like that, and they would also be saved, and so that I could use the same values when I analyze and make these plots. So that's also one of the things that I had to add to the features. And then when the items and their respective values are set, the max constraint is set within the loop, Yeah, that's about it. Let me just take some water. So when after I have saved the values for the items, I just wanted to quickly show the distributions. So 50 items and two sets of 50 values, utility values and constraint values were respectively generated, and the first pair is just that, meaning utility value normal, constraint values normal. The second pair is the second iteration. Utility values were normal and constraint values were log normal. The third one is normal and uniform. The fourth one, normal and expovariate. Fifth, normal and von Mises. Sixth, normal and Pareto. Seventh, normal and Weibull. Eighth, normal and left skewed. So this is what it looks like. Although I've said that normal and left skewed look kind of quite similar, even more than kind of similar, but if you were to plot the KDE plot, you see the slight difference there. It is still kind of left skewed, and so this is just a way to illustrate the the distribution of values that were used for the 64 evolutions, 64 evolution iterations. And that out of the way, we'll have a look at the final world entity distributions, where I used the Seaborn histogram plot, hist plot for this, and the bins, the number for the bins was 200, so that the numbers or the counts don't just stack up too high, so that I can compare the plots that I got here from the other previous plots. So actually I said that wrong. It shouldn't be bins 200. I also have that at 300 as well. This is the right one. And if you look, for example, look at where my cursor is. See how it got higher when the bins got lower, from 300 to 200. Now back to 300, it got lower. Everything got lower, kind of. So I'm just going to stick to 300 for now, and from the previous videos, it was this one. Yeah, from this, I said that I would stick to learn rate, proportional head, proportionate tail, and exponential candidate method, exponential tail. This one. This is what I said I'd be using. This one, because I wanted I wanted the shapes to be like this. Exponential head, exponential tail. No, let me just find that again. There we go. This is what I wanted, and the purpose of having the world entity distributions from the general genetic algorithm was to see if I could see the similar shape of this distribution on these results. Because for the preset 50 items, for the 50 items that were preset, they were kind of log normal in terms of distribution. But in this case, they're not log normal. it's a whole army of distribution combinations. So yeah, I felt that I needed to do this. And just a general overview, you could probably see that they are quite similar to this one on the right. Yeah, the only variations or the difference between these between the results of these combos is how close the cluster or the well, the whole shape is to the red line, because the red line is the sum of all utility values, which means that the red line can only be touched, or it can only be truly touched or met by any entity only when that entity has no max constraint limits, meaning that only when that entity contains all the items. So depending on what distribution combination the problem space dictates, the distance between the cluster, the bell shape, or whatever, the entities, or where the head entity is, for example here, the difference between the head entity and the red line is different. For instance, if you look closer here, this is very close. This is quite close, whereas this is quite far. This is, oh yeah, this is also very far. Look at that. See how normal distribution and left skewed kind of look similar? So diagonally speaking, that's when both the utility values and the constraint values are sampled from the same distribution. So this is normal, log normal, uniform, I guess. Yeah, uniform, expovariate or exponential, von Mises, Pareto, Weibull, and left skewed. Yeah, so it's quite apparent that that is about the most interesting thing here, the distance between the head, where the head entity is, and the red line. And well, I guess that depends on the ratio or the respective ratios between the utility values and the constraint values, and these gaps will probably tend to be closer if the well, if the constraint values are not really normally distributed. Yeah. As in, look, if you look at Pareto here, this is also very close. Maybe not. Oh yeah, look at that. Von Mises. Folks, let me just look at the distributions. X variable Mises. No, which line is that? Either 1, 2, 3, 4. There we go. So from this came this. From this came this. See, this is not evenly distributed or normally distributed values. This is not what normally distributed values look like. So as long as the constraint values are concerned, and when that happens, what you can do is the entities will tend to, well, take the, well, they'll kind of automatically or naturally start taking items or activating genes that have well, a good bang for buck, I might say, good efficiency. So if, for example, if the utility value is 100 and the constraint value is 20, that's 5 to 1, then you might have another item or gene that gives you a utility value of 50, and the constraint value is 2, that's 25 to 1. So many entities will end up taking that, and what happens is that when that happens, the step towards the step towards the red line gets smaller and smaller, or rather the gap between the red line and the head entity gets smaller, because the head entity is likely to have all the utility, all the genes or items that have good utility to constraint value ratio, and they're likely to not have the ones that give you a poor bang for buck. But it is interesting because the max constraint percentage was set to 75. That's 75. But when I have this, it seems, when I have a plot like this, it seems that 75 or that 25 percent that cannot go into entities don't really seem to matter, because there's only this much of a gap, this small gap, when something like this happens. Whereas here, yeah, I mean, I think that 25% that cannot go into the entities in terms of constraint values is well represented. Even here, oh, even more so. This is odd. But then again, things like this used to happen, or used to happen before, it happens now, and I think it happens usually when the values are if the values somewhat follow a normal distribution, or something like normal or something that even partially may behave in that instance like a normal distribution. So yeah, that's it. And one last thing is the summed utility over generations, or summed utility plots for the world over the generations. Well, this is like almost the same thing, except now we get to see this is until generation 500. Well, one thing to actually note, or one thing that we should point out or I should point out and be kind of glad or proud, is that there are no dips. I mean, maybe somewhere here, but that's not a dip. That's not exactly a dip. And the top 10%, which is the magenta line over here, is very close to the red lines, which is the heads. And the heads almost always touch the black one, the black dash dotted line, which is the maximum ever, maximum ever of any entities that exist or may have existed, or no, that exist or have existed. And the red line very frequently gets there. This is the power of, this is a result or the power of a better evolution scheme, shuffling and learning. Yeah, I think that's about it. And learning, and of course to learn you need to select the candidates as well. So those are very interesting things to take note of. Other than that, this is nothing that we haven't seen so far. It's nice to know that the same findings from the few previous videos that I have done kind of all apply here as well. Maybe it's because I made it that way, but I didn't actually make it that way. Maybe I did unwillingly, unintentionally. But so far, I'm sure I haven't found anything that I feel that I have led things to be this way. But anyway, I might find 1 or 2 or maybe 10 mistakes in the future, but for now I'm okay with that. So this is until generation 120. The first line is where the utility values are from the normal distribution. The second line, log normal. Third line, whatever. And the first row, the first column here, first row was that, and first column here is where the constraint values are from the normal. Second column, log normal. Third column, uniform, and so on and so on, and blah 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 blah. And again, the diagonal ones are where the uniform, where the utility values and the constraint values were sampled separately, but still from the same distribution type. You'll see that because the candidate method is, or even when the candidate method is exponential tail, the learning seems to apply to to a satisfactory degree to the bottom entity, or bottom entities, the tail entities, which are these blue lines. This blue dashed dotted line is the plateau, which is this, which is not the same as the plot, this squiggly zigzaggy line for the tail entities. I know I could have assigned another color for this, but I didn't. My bad. Anyway, so the learning does seem to apply, and the shuffling does seem to work. The better evolution algorithm does seem to still work, even after the learning and the shuffling. And even after shuffling, and then they all work even when I'm doing general genetic algorithms with generated values. That's a mouthful to say. They actually work somewhat too well, because they really do converge all the time. Look at that. Oh, look at this one. The magenta line, which is for the top, which is the average of top 10%, and the red line, which is the head entities. So that's just one entity per generation, whereas the magenta line is somewhere close to 100 entities, you know, ever since this point. So it's 90 to anywhere from between 90 to 100 entities. It is quite astonishing that the average of around approximately 100 entities is this close to the top, the head entity. They're off by this much, which didn't used to happen when I mean in my previous videos. See, it's almost touching. But then it is almost touching, but at the same time I don't have a very squished distribution. Yeah. So I think that's good. So that's about it for this video. Well, I've just covered all the material that I wanted for today, or for tonight rather. Well, I do need to start working on dynamic genetic algorithm, making things dynamic. It goes from here, it goes dynamic, and then maybe dynamic general. But anyway, the dynamic part is the crucial part, and then it goes on to chaotic. Yeah, chaotic is when everything just happens all at once or never happens. We'll never know. And all at the same time. Or quite simultaneously, all at the same time, I don't know. And then maybe when that is done, it could also be interactive as well. I'm always opening a new can of worms. Okay, thanks for watching. Bye.